Picture this. You open your mock exam paper, flip straight to the algorithm section, and there it is, the dreaded red pen. You lost marks on a question you swore you absolutely nailed. I mean, you knew the content, you memorized the symbols, but the examiner still didn't give you the full grade. What gives? Well, if you're tired of losing crucial marks just because your answers are a tiny bit off what the mark scheme demands, you are in the exact right place. In this explainer, we're going completely undercover as data detectives. We're going to decode the precise technical language and logic that Cambridge examiners demand, taking you from a risky grade boundary to absolute top band safety. Let's dive in. Right off the bat, this is one of the most painful and common learner mistakes we see. I drew the flowchart shapes, but I still lost the marks. It's a massive trap. Relying on just rote memorization of simple shapes without actually understanding how they string together logically, that is a huge grade boundary risk. The examiners aren't just looking for a pretty drawing, they're testing your computational thinking. If you just guess the shapes without rigid logic, your entire algorithm completely breaks down. Okay, Section 1, the one-mark exam trap. So let's investigate why standard, casual revision completely fails against the examiner's trap. It really all starts with the terminology you use. The difference between a generic answer and a top-band answer is incredibly slim, but it literally represents the gap between an average grade and an exceptional one. To see what I mean, just compare a generic answer to a top-band one. When asked about structure diagrams, a generic student writes, "It breaks down a system." And guess what? That gets 0 marks. Why? Because it's conversational, it's not computational. Now, look at the exact Cambridge technical phrasing: decomposition of a computer system into subsystems in a top-down diagrammatic form. That is what examiners actually demand. They want the specific nouns and adjectives: decomposition, subsystems, top-down, diagrammatic. You aren't just writing an answer, you're proving you speak their language. Moving on to Section 2, 4 vital flowchart symbols. To speak the examiner's language, you need the right tools. And in algorithmic problem solving, those tools are your standard flowchart symbols. Let's build our basic data detective tool belt so we can decode these questions properly. You see, every specific pseudocode statement has a rigid diagrammatic equivalent that must be used correctly. We've got 4 vital components here. First up, flow lines. These dictate the strict sequence of execution. Second, assignments, usually depicted by a rectangle where a calculation is made or a value is assigned to a variable. Third, input-output, the parallelogram where data enters or leaves the system. And finally, decision logic, the diamond, where your program branches based on a true or false condition. You absolutely cannot mix these up. An assignment cannot happen in an input box, no way. But here's the thing, knowing those 4 shapes is literally just step 1. There's a highly specific clue examiners look for in loop flowcharts that changes everything about how your code runs. Miss this one tiny detail and your entire program fails. But before we get there, we really need to secure your foundation of how loops actually function. So keep that hidden detail in the back of your mind. We're going to uncover it in just a second. Section 3, pre versus post condition loops. Let's escalate the stakes a bit by applying our symbols to a real complex loop scenario. We aren't just drawing shapes anymore, we're managing data dynamically. And this brings us to the crucial battleground of iteration. This brilliantly illustrates how a simple array of 20 students completely changes depending on exactly where the counter is tested. First, we have a precondition loop. Here, the counter is tested right at the start of the loop. If the condition isn't met, the loop might never execute, not even once. Then we have the post-condition loop. The counter is tested at the very end, meaning the code inside the loop will always run at least once, no matter what. Imagine you're processing an array called student 0 to 19. If you use a post-condition loop when a precondition was actually needed, you might accidentally process an empty array and crash your entire program. And that is the exact clue examiners are hunting for. Did you put the decision diamond at the top or down at the bottom? Section 4, escalating the stakes with logic circuits. Now let's see how this builds when we jump from basic algorithms into hard logic circuits. Because data detectives don't just work in software, right? They track digital logic in hardware and control systems too. The crucial point here is how these specific real-world parameters map perfectly onto binary truth table conditions. Let's say we're monitoring a dangerous chemical process. We have reaction temperature T, pressure P, and acid concentration A. Notice how continuous analog data is basically forced into strict binary states. If the temperature is greater than 120 degrees, the binary value is 0. If it's less than or equal to 120, it's 1. The exam is going to give you this table, and your job is to translate these real-world constraints into an ironclad logic expression. Let's see exactly how that comes together. So here is the exact scenario. Alarm X sounds if specific, highly dangerous conditions are met. It triggers if temperature is greater than 120 and acid is less than or equal to 4, or if temperature is less than or equal to 120 and pressure is less than or equal to 2, or if acid is greater than 4 and pressure is less than or equal to 2. Wow, okay. You have to track this data like a detective. You look at the binary ones and zeros from the previous table and swap them right into this exact logic statement to build your logic gates. If you miss a single and or a single or, the chemical plant metaphorically explodes, and well, your exam marks go right up in smoke with it. Okay, time for a rapid checkpoint. We're going to simulate a bit of exam pressure and force you to actively retrieve what we just covered. So, pause and solve this question. Which loop counter tests the condition before the logic executes? Is it a precondition loop or a post-condition loop? Think about it, lock in your answer, and the answer is the precondition loop. If you got that right, awesome, you are successfully tracking the logic. The decision diamond sits right up at the top of the flowchart. If you missed it, no worries, just remember, pre means before. All right, section 5, the mark scheme answer upgrade. Welcome to the clinic phase. We are going to transform our newfound knowledge into actual usable exam strategy. Because honestly, understanding the logic is only half the battle. Writing it down exactly how the examiner wants it is the whole other half. First, let's secure these Cambridge safe definitions, because imprecise wording here is where most students just hemorrhage marks. A global variable can be used anywhere in the program. A local variable is declared within a specific procedure or function. Actually, scratch that. It's not just declared there. It ceases to exist once that procedure finishes. If a question asks you to compare them, you absolutely cannot just say one is big and one is small. You must use the terms anywhere in the program and declared within a specific procedure. To guarantee you hit those top bands, I want you to use this ultimate 4-step framework for upgrading a weak answer into a totally flawless response. Step 1, provide the exact definition. Step 2, explain the mechanism, like how does it actually work in the computer? Step 3, apply it directly to the scenario given in the question. Use their specific nouns like the chemical plant or the student array. And step 4, use precise examiner wording to lock in the marks. This structure basically forces you to be thorough, logical, and computationally accurate every single time. And finally, section 6, your next exam clue. We've covered some incredibly serious ground today, moving from standard shapes to preconditioned array loops and even decoding complex logic circuits using our brand new 4-step answer framework. To make sure you never miss a critical exam strategy, definitely subscribe to our channel, Ace the Exams, at acetheexams_IGCSE. It's an absolute must-have in your exam success toolkit for sure. So, we've cracked the logic, and you now know exactly how to build flowcharts and logic gates. But what happens when your logic is absolutely flawless, but the data being fed into it is completely corrupted? How do you track a ghost in the machine? There is a linked data analysis skill that you absolutely must master for full marks on paper 2. The final clue to complete your data detective training is waiting for you in our next explainer. Go ahead and click over to it right now, and let's finish the job.